Our goal is to head towards derivatives. Now, last time we talked about limits. And it's not so unusual to think that limits and derivatives should be involved. When we think about the single variable functions, when we talked about derivatives, that's how we defined derivatives, was as a limit. The limit as x goes to a of f of x minus f of a over x minus a. And we want to talk about what happens with multivariable functions. Before I get too far down the road here, you may say, you know, you left off a strategy. Because we talked about things like approach from different directions and see what happens. If it's continuous, plug it in. We talked about squeezing. We said take more math classes. But we seem to have left out one of our favorite ways to take limits. Do you know what I'm talking about? Well, it's the L'Hopital. You know, the L'Hopital. You know, why don't we do that? The answer is we can't. The L'Hopital works when you have a single thing you can vary. So in other words, a limit as, say, t goes to 0 or as x goes to 0. But if multiple things are changing, x and y are both going to 0, L'Hopital is out. So there is no more L'Hopital. Well, it was good while it lasted. Okay, all right. So just be careful. Now, that isn't to say that you'll never use it. You could, for example, use it. One of the things we talked about is as you approach a point. You know, from approach, say, along an axis, what happens is you're going from sort of two things varying. When we approach along a parameterized line, we get down to one thing varying. Now, when you're back in that setting, it's okay. So it's not, it might show up from time to time on a quiz problem, for example. All right. Anyways, back to our regularly scheduled lecture. We know how to take derivatives in single variable calculus. So let's just sort of say, okay, let's do some guesses about how we should take derivatives. And I have two guesses here, so let's go through them. Guess number one. Well, what's the idea? Here, when we looked at our derivative, we said what the derivative is doing is it's looking at the change, which we use a capital delta to represent change in the output over change in the input. How much is my output changing as I change my input? That's the derivative. So a first guess, a very reasonable guess, is let's do the same thing. Change in output, well, that's basically the obvious thing, f of xy minus f of ab. Change in input. Well, now we have to say, what is this? What is this term down here? When I talk about xy minus ab, what would it be?
Vector.
It would be a vector. Now, we ask ourselves the question, does this make sense to have a number divided by a vector? No, it doesn't make sense. We can barely multiply. Hashtag epic fail. Okay, just not going to work. Not going to work. Well, the problem is it's a vector. So let's do something different. Let's look at the change in the output over the size of the change in the input. Just like I'm taking the norm of the vector downstairs. Does that make sense? Is that going to work? Well, the answer is no. But it's not an epic fail, it's a subtle fail. Now, what's wrong? Why does that fail? Because it seems to be like, okay, I'm looking at change in output over change in input. And here's the answer. Math, and in particular when I say math, I really mean calculus, there's an orientation involved. So when we talk about numbers, there's an orientation to the number system. You have increasing, things are getting more positive. You have decreasing, things are getting more negative. So there's an orientation built into the number system, and orientation matters. When you take this magnitude, you're stripping away the information about orientation. So this won't work. And it's not hard to sort of go through examples to say you're getting very strange things which shouldn't work. So okay, so how do we actually take derivatives? Well, here's what we're going to do. We're going to work in cross sections. So this is the picture you should have in mind. So if I have a function, so you should think of this as there's this surface here, and I'm just sort of outlining a piece of the surface. So this is a function. So recall that when we talk about function z equals f of x, y, you can represent them graphically as surfaces. And so I say, okay, what I can do is I can come along and I can slice. So here, you can see I've taken a slice, and what I've done is I've fixed my value for x. So in other words, I say I'm going to fix x to be some numerical value. Maybe it's 2, maybe it's 5, it doesn't matter. But I'm fixing x and I'm taking a slice. Now why do I want to do this? Well, once I take a slice, because x is fixed, nothing depends on x anymore. X has been chosen for us. So what I can see is that, lo and behold, I now have a relationship between y and z. So I've taken this slice and I said, look at it in the yz plane. Well, what am I down to? Well, now I'm down to z depending on just what is y doing. And I can talk about how does z vary as I vary y. Because here now, remember, x is fixed. There is no more x varying. So now we can answer questions about what's happening over here. So in particular, I could say, well, maybe there's a point. I don't know, there's my point. Well, in the slice, again, it corresponds to a point. And I can say, what's happening? Well, there's some tangent line. And I can find that tangent line. And that tangent line gives me information about the rate of change. And you're saying, well, this is great. But what's the real answer? How are we really going to take derivatives in our class? And the answer is, that's it. That's how we take derivatives. We go back to the tools that we have. Now, it may or may not be very satisfying. The good news is you don't have to learn new techniques. All the things that you learned in your previous calculus classes are still going to work. So what we're really doing is multivariable calculus is single variable calculus with extra steps. You just do it multiple times. Now let's talk a little bit about what's going on. So in particular, what's happening here, this picture we fixed x, and so if I have that the surface is my f of xy, now when I think of x fixed, my cross section, I can say, look, it's down to just a function of a single variable down to a function of y, and I take its derivative, g prime of y. And you just do what you would normally do. Plug it into the definition of the derivative. Changing the output over changing the input. But of course we know g is really just f of x comma y, where x is fixed. So you put in f of x comma y plus h minus f of x comma y all over h. And that is called the partial derivative of the function with respect to, whoops, why did I put an x there? That's a typo. That's with respect to y. All right, fix that in post-production. How is the function f changing as the y input changes? Now, that is, I sliced and I fixed x. What could I have done? Is there anything else I could do? I could fix y. So if I fixed y, I would be getting a different kind of slice. So it's the same process, though. We hold y fixed. We have a function of x. We'll call it kappa of x. And we run through, and we get what's called the partial derivative of f with respect to x. Now, the reason we call this the partial derivative is we're asking how is the function changing as we change part of the input, because there's multiple inputs. And so we're in this case, we're either saying how is it changing with respect to the second input, y, or how is it changing as we change the first input, x. So the moral is we take these derivatives one variable at a time. Okay, so let's talk a little bit. Here's another example, a surface. And we'll come through and draw a lot more of this in class next time. But again, what do I have? Is I have this surface. Z is my function, x comma y. And I'm looking into my cross sections. And I can either hold y fixed, and I get the picture shown here on the left, or I can hold x fixed, and I can get the picture shown here on the right. Now, what I want to emphasize with this particular drawing is to say, look at the behaviors. If I look where y is fixed, and I were to draw a tangent line, what can you tell me about the slope of the tangent line? It goes down. So the derivative would be a negative value. What about over here? What's the slope of the tangent line? It's positive. It's going up. So when you look in the slices, their behaviors can be very different. So you don't say, I understand what's happening when I take the derivative with respect to x, so now I understand the derivative with respect to y. No. You have to do both separately because they'll behave in different ways. So you have to be careful. And we should point out that the tangent lines actually can be represented back in our original picture. So what is this tangent line? Well, this tangent line is just touching the line here in the xz plane. Well, up here I can translate, and I get a line that's here in 3 dimensions where what's happening is y is fixed. It's the same line, just introduce a fixed y component. Well, similarly, I can come to this tangent line, and I can represent it in the picture. It's a line which is tangent right here. So I can find these two lines now in 3 dimensions. Well, what comes next? If I have the two lines, what's the next natural thing to do? Make a plane. Yeah. Next natural thing to do is to make a plane. And that is what we'll do next time. But for now, I want to focus on partial derivatives. I want to keep on track. So let's talk about our notation. So you'll notice that we've actually introduced some new symbols. So if you go back to what we had on the previous page, we talked about these partial derivatives. There's a symbol here that's a little different than what we've used to use. It's not like a D, it's something a little different. So that's called the partial symbol. So what do we have? Well, both these symbols are indicating a derivative. So when do we use them? So we use the letter D to indicate a derivative when we're taking the derivative of a function of a single variable. So when our input, or rather I should say the output, only relies on a single input, that's a function of a single variable. And if I see a function of a single variable, I'm going to use D. And we're going to be consistent about that from here on. So when we ever have a single variable function, that we use a D. When my function depends on multiple variables, well, now I switch and use the other notation, which is the partial symbol. So that's in this way. And so to help you master how do you write the partial symbol, it's done in the following way. All right, so we'll put a little box here and take you back to your first grade class when you had to follow the arrows. Start at the top, work around, and stop. Don't go through, stop. So it's not like a badly written 2. No, you're supposed to stop. Okay, so you should become very comfortable with writing this symbol, because you're going to write this symbol a lot in this class. I hope you already know how to write the letter D, so I won't go through that one. But okay. So that's the difference between the two. They both indicate that there's a derivative involved. So when you see either one, think derivative. The symbol indicates single versus multivariable. Now, if we go back to single variable, there was a convention that said I could have written this as df dx, changing my function f with respect to x, or I could write it as f prime. Because we write it so much, we oftentimes say, well, f prime is more convenient to write. We'd like to have that be true again. So I'd like to write f prime, or something like it. Because, okay, I'm taking a derivative, and so the natural thing to guess is to say, aha, I'm taking a derivative, so I should write this as like f prime. And, oh, I took a derivative here, I should write it as f prime. But what's the problem? I can't use the same notation to represent two different things, because the partial derivatives can be very different. We've seen this over here. The partial derivatives with respect to the different variables can have very different behavior. So this, unfortunately, is a notation that we're going to drop. We're no longer going to use primes to indicate derivatives. So how are we going to do it? Well, what do we need to do? We have to indicate which derivative we took. So here's the new notation. We put in subscripts. So if I'm taking the derivative with respect to x, f sub x. If I'm taking the derivative with respect to y, f sub y. And that's our notation. So when you see these subscripts start showing up, that's an indication that, aha, we're taking derivatives, and the subscripts are telling us what kind of derivatives that we're taking. All right. Well, that's the theory. Time for practice. Any questions before we begin? Oh, there's a question.
What if you want to take like multiple derivatives, like f double prime?
Yes, good question. We will get there in a few moments, but you can. And you'll need to for things which are to come. That's about 2 weeks away from now. Ah, good times, good times. Yes, we'll get there, we'll get there. All right. So, rule of thumb, and as long as you remember this, it's pretty easy to take partial derivatives. When we're taking a derivative with respect to some variable, everything else we're going to treat like a constant. So even though, yes, x and y are variables, when I'm taking a partial derivative with respect to one of them, I'll treat the other one like a constant. So there's an example here. Find partial f partial x, where f of xy is the following function. X squared plus x times arctangent of y plus y to the power 137 e to the power sine of log of y squared plus 7. Now, normally, this would start to make us a little nervous. Oh, lots of chain rule coming up, power product rule, all sorts of crazy things coming up. Or is there? Let's think about it. Partial f partial x says take the derivative with respect to x. So this notation is telling us what derivative we want. I have, this is a function of x and y. When I'm finding partial f partial x, what am I going to do with the y's? Hold them as constants. So we go through derivative of x squared with respect to x, 2x. Now notice I'm adding a phrase. I didn't ask, what's the derivative of x squared? I said, what's the derivative of x squared with respect to x? Because now we have to keep track. This is where the multivariable, you got to start saying, okay, keep in mind, what am I taking the derivative with respect to? The derivative of x times arctangent of y with respect to x. Yeah. So essentially, from the perspective where x is what's varying, I have this part which is varying, the x. The arctangent y is not. It's like a constant. And the derivative of a constant times x would be that constant again, plus arctangent of y. Well, what's the derivative of y to the 137 e to the sine of log of y squared plus 7 with respect to x? 0. Why? There's no x. If there's no x, it doesn't change as you change x, and therefore there's no change. It's 0. That was nice. If only we could have those for the test. Well, come on, we want something more fun. Okay. So now let's do another one, but you get to pick the function. And we'll find both partial derivatives. Notice here, I'm switching notation. Partial f, partial x. Now I say g sub x. So you should be familiar with both notations. Okay, g of x, y. I need a function. Okay, so give me a function that we can work with. I need a more interesting function. Okay, we'll have x divided by y to start us off. What else?
Plus ln x plus y. ln of x plus y.
ln of x plus y. All right. Anything else? You can have fun.
Plus 1.
Plus 1. Is that really fun? All right. Arctangent of x. Okay, people are trying to pander now. How about let's throw an x to the y? Let's see if you can do that. Okay, so let's find them both. All right. First up, let's do g sub x. So we're going to go through each term. G sub x. The derivative of x over y. 1 over y. That's right. The 1 over y is constant. It's essentially constant times x. The derivative of natural log of x plus y. 1 over x plus y. And of course, if we did the chain rule, times the derivative of x plus y, which is 1. Derivative of 1, 0. Derivative of arctangent of x, 1 over x squared plus 1, or 1 plus x squared. Derivative of x to the y.
yx to y minus 1.
Yx to the y minus 1 is correct, because it's x to a number. You got to think of which rule you're using. So derivative of x to a number, bring the exponent down. So that'd be y. X to 1 less. Yx to the y minus 1. Okay. Good. All right. That one's not so bad. Well, how about g sub y? Okay, let's go through it. Derivative of x over y. Minus x over y squared. Now, how do you do that? Well, another way to write x over y is as x to the y, x times y to the negative 1. So x is a constant. That stays there. Derivative of y to the negative 1. Negative 1 comes down. Y to the negative 2. And so I forgot the 2. Thank you. Derivative of natural log of x plus y. Oh, I goofed. I should have said derivative of natural log of x plus y with respect to y is 1 over x plus y. But wait a second. Isn't that what we got when we took the derivative with respect to x? Yeah, okay, there's symmetry here. It's okay. Derivative of 1? 0. Doesn't matter whether it's with respect to x or with respect to y. Derivative of arctangent of x with respect to y? 0. Derivative of x to the y. Now this one might stump a few people because they might not remember the rule. Does anyone remember the rule? It starts off as x to the y. And then natural log of x. So the rule is, you might remember this rule. We'll put it over here. if you're taking the derivative of a to the power x, it's a to the power x times the natural log of a. So like derivative of e to the x is e to the x. Well, it's really e to the x times the natural log of e, but the natural log of e is 1. And that works for any base a. Now in our case, here, when I'm taking the derivative of x to y with respect to y, essentially I have a number to the y. So this x is acting as my base a. And so that's how I applied the rule. All right. So we can take these derivatives. Now that's two variable functions. It works with any number of variables. 2 variables, 3 variables, 4 variables. And you don't have to use the letters x and y and z. You can use whatever letters you like. So I could have a function of x and y and t. This is not uncommon. In fact, a lot of times this is how we think of things. We say, okay, it depends on your location and your time. X and y is a location, and t is a time. A lot of processes can be described this way. So give me a function.
Cosecant squared of 7x.
Okay. All right. Cosecant squared of 7. Now we're not integrating. Keep in mind we're taking a derivative, but all right. Should also have y's and t's in there at some point. Okay. Well, I'll start throwing things in. X squared y t cubed. Anyone else want to contribute something?
E to the y times sine of z.
Well, e to the y sine of t, something like that.
Sine of t times y. The sine of t is a power.
Okay. Maybe like that?
Yeah.
Okay. Great. Good. All right. So, find, and you'll notice the word here first. Well, that leads into a question we had earlier. We'll get into that answer in a second. All right. So, you asked for it. Derivative of cosecant squared of 7x is negative 14. Right. What comes next? Cosecant squared, but okay, of 7x. Cotangent. Okay, very good. All right, good. You know your derivatives. Now you're probably thinking, how did he get those numbers? Okay, let's talk about where numbers came from. If you're taking the derivative of cosecant squared, what rule do you need to use? Chain rule, because it's the cosecant inside the square. It's actually the 7x inside the cosecant inside the square. So it's like double chain. All right. So the 2 comes down. You have cosecant of 7x to the 1. You're probably thinking, oh, you made a mistake. You put cosecant squared. I'm not done yet. Times the derivative of cosecant. What's the derivative of cosecant? Negative cosecant cotangent. So that's where the negative came from. So that's where my second cosecant came from. That's where my cotangent came from. And then where did my 7 come from? Because I got to 14. Multiplied by 7 by the chain rule. It's all there. Good. And, well, except I'm running out of space. Okay, plus. What's the next term? Derivative of the next term with respect to x. 2x y t cubed. And what's the derivative of e to the y sine t with respect to x? 0. Done. Done. Okay. Well, with that derivative. See, this is like fun times because it's one derivative at a time, you know. It's like a single problem, but I get to do 3 derivatives. The dream. We're living the dream. Okay. Derivative of cosecant, next variable, y. Cosecant squared 7x with respect to y? 0. X squared y t cubed, derivative with respect to y? X squared t cubed. Derivative of e to the power y sine t with respect to y? Sine of t, e to the y sine of t. Because it's e to the y times a constant. So the derivative of e to the y times a constant is e to the y times a constant times the derivative of the exponent, which would be that constant, in this case the sine of t. Okay, h sub t. All right, derivative of cosecant squared 7x with respect to t, 0. Derivative of x squared y t cubed with respect to t, it should be the 3, because that's the part attached to the t, so 3 x squared y t squared. Derivative of e to the power y sine of t with respect to t. What is it?
E to the y sine t times cosine t.
Okay, so it's e to the y sine of t. And what does it get multiplied by down below? Y cosine t. Yeah, so the derivative of y times sine of t is y times cosine of t, when I'm taking the derivative with respect to t. All right. Now, we were asked, what about higher order partial derivatives? These are really derivatives of derivatives. And we can go as far as you want. So these would be, if I have a function f of x, y, there are 4 second order derivatives. Second order means I took 2. And I'm listing them all. And I'm showing you the various notations. So we'll just read off. Partial squared f, partial x squared. Well, this is a second derivative. Well, they're all second derivatives. That's not a surprise. But what is it? It's saying take the derivative with respect to x of whatever you get when you take the derivative with respect to x. Now, in terms of subscript notation, fxx. Or you could say partial squared f, partial x, partial y. Well, that says take the derivative with respect to x of the derivative with respect to y. Now, how's the subscript notation? fyx. Now, you might say, whoa, wait a second. These seem to be going in opposite directions. And you are correct. One of them goes left to right. One of them goes right to left. Why? Well, we like to confuse people. No. There's sort of an idea of sort of an order of operations, which one comes first. Now, you might say, does it matter? Well, for instance, this says taking the derivative first with respect to y, then with respect to x. This says take it with respect to x, then take it with respect to y. Can they be different? The answer is yes, they can. Will they be different? No, they won't. So, for nice functions, and we will only introduce you to nice functions. Those are the only kind you'll see. These match. So what does it mean to be nice? Well, it means that you can take enough derivatives. So the types of functions that you'll encounter are going to be the nice functions. I think if you look in your book, you'll see an example of a not nice function. So in particular, for most functions, order doesn't matter. We'll check an example in a moment here. The other derivative you should be aware of is the second derivative with respect to y. Now, that's the second order derivatives. Can you go further? Yeah, you can take as many derivatives as you want. So, here's an example. I have a function of x, y, and z. So, here's a derivative. Let's see what we can gather. Now, some things you should note. Hopefully you've cracked the code. This here, that's the number, partial 5. That tells you how many derivatives you've taken. So this is a fifth derivative. The exponents down below, it's really a 1, 1, 1, and a 2, tell you how many of each type. So this says what? Well, take 2 derivatives with respect to z, then a derivative with respect to y, then a derivative with respect to z, and then a derivative with respect to x. In that order. Now, of course, for most functions, it doesn't matter. So if it's a nice function, we could have rechanged the order, and we could have said, well, let's take 3 derivatives with respect to z first. Now, if we write it in our subscript notation, we'd have a z, z, y, zx. Z, z, y, zx. Now, you might think, if only there were a word that you could spell using the letters x, y, and z. And the answer is, that's the word. Zizix. You might think I just made that up. It's a place in California. Now, if you live in Southern California, for example, San Diego or Los Angeles, and you want to go to Las Vegas to do some applied probability, while you're driving on the road to Las Vegas, you will pass a sign that says Zizix Road. It's a real place, and nobody really goes there, but it exists. And it's the exciting thing because the next thing means that you're going to be in Nevada. So you get excited when you see that sign. It's also, there's a movie called Zizix. It made $30 at the box office. So nobody went and saw it. But anyways. But the point is you can take higher order partial derivatives. Generally speaking, we're not going to worry too much about higher orders, but we will worry about second orders because that's going to be important when we start talking about optimization, and that will be coming very soon. All right, so let's do some second order partial derivatives. Find all second order, which means that there are 4 partial derivatives for f of xy is x squared e to the xy plus y cosine of x. So let's work our way through this. So here's my function. If I want the second order partial derivatives, what should I find first? The first order partial derivatives. We've got to work your way up to it. Okay, so f sub x. And I'm going to suppress the of x and y. But I'm going to just say, look, they're always there. Okay, so let's go through. Derivative of x squared e to the xy with respect to x. What rule will I need to use? Product rule. Because I have 2 things changing, the x squared and the e to the xy. So the derivative of the first with respect to x, 2x, e to the xy, plus, go to the next one, x squared e to the xy. Well, what do I get? What do I write down? It would be x squared y e to the xy. Here, the derivative of e to the xy, take the derivative, I'm taking it with respect to x. The y acts like a constant. So if I had e to a constant times x, it would still be e to the constant times x, and then the constant comes down. All right, derivative of y cosine x with respect to x, minus y sine of x. Now, derivative of f with respect to y. Well, x squared e to the xy. Do I need the product rule? No, I don't. Because I don't have 2 things varying. Only one of those 2 things vary when I vary y. So what is the first thing I write down? What is it? X cubed e to the xy. Now, how did x squared become x cubed? Well, you're going to add another x when you're taking the derivative of e to the xy. What's the derivative of y cosine x with respect to y? Cosine x. All right. Now the first derivatives are done. Okay, so let's go through it. Find the second derivatives. F sub x x. All right. Well, now we're just sort of like a, okay. We're going to need a product rule here, and product rule here, and that won't be so bad. So in the interest of time, I'm just going to talk while I take this derivative. So here it's just, the key is be patient. And don't try to rush. So I take the derivative of the first times the second. Then I have 2x times the derivative of e to the xy, which will be y e to the xy. So that's the derivative of the first term. Next term, well, derivative of x squared, 2x y e to the xy. And you might say, whoa, those match. Not a coincidence. They actually should match. That's a different story. That's a Calc 1 story. It's a lovely story. Then derivative of x squared y is constant times derivative of e to the xy, x squared y squared e to the xy. And I ran out of space, but the next part would be minus y cosine x, taking derivative with respect to x. All right, so that's derivative f of xx. Now, fxy, go through, take derivative with respect to y. The first term, well, there's only one y, so that's good. So it's going to be 2x. Derivative of e to the xy will bring another x down, so 2x squared e to the xy. The next term, I'll get x squared times y. Derivative of that will be x squared. And then I'll have e to the xy plus x squared y times the derivative of e to the xy with respect to y, which will give us x cubed y e to the xy. And then the derivative of minus y sine of x with respect to y will be minus sine of x. On the other hand, if I took f sub y x, what would I have? Well, product rule, x cubed e to the xy would be 3x squared e to the xy, because I take the derivative of the first part with respect to x. That's the x cubed. Then I'm going to add to that derivative of x cubed e to the xy. So it'll be x cubed times the derivative of e to the xy with respect to x, which would be x cubed y e to the xy plus the derivative of cosine of x with respect to x, which is minus sine of x. Now, I seem to have run into a quandary because I said that the two partial derivatives, it doesn't matter what order you take them. So why do they look different? Well, they look different. Are they different? They're not different. So one of the things you have to pay attention to is, yes, it's true that order doesn't matter in terms of your answer for nice functions, which again, those are the kinds you're going to see. However, that being said, it can make a difference for how much work you do. So sometimes if you take the derivatives in a certain order, it's a lot less work than if you were to change the order. So think about it. Occasionally, and there have been examples like this on past exams from a long, long time ago, where we gave a function and said, well, take the second order partial derivative. And if you took it in the right way, very easy, done in 30 seconds. If you took it not the right way, it took more than 30 seconds. But that's a different story. Okay, rounding the corner here. F sub y, y. Well, what do you get? X cubed e to the xy, take the derivative of that with respect to x, you end up with x to the fourth e to the xy. Derivative of cosine x with respect to y, 0. Doesn't depend on y. So you can see that these are different. The fxx versus fyy, they're very different types of functions. So you have to do the work. You have to do the work. Now, last thing to talk about for today, this notion of partial differential equations. So we talked about differential equations in Calc 1 for just a day or two. We said, well, what's a differential equation? The idea is I have some relationship between my function and its derivative. All right. Well, what's a partial differential equation? Well, it's a relationship between my function and partial derivatives. Now, partial differential equations are a very important topic because most things that people are concerned about, for example, in physics, you care about two things. How am I changing with time? Which means I need to keep track of time, but the other thing is I'm actually somewhere, which means I have to keep track of space. So I have space and time. So partial derivatives are the right setting for most of the things that we're interested in. Now you might be like, oh, that's great, because I'm scheduled to take a class called differential equations. And I'm going to learn all about this stuff. But I will let you in on a little bit of sad news. When you take differential equations, you're not going to be studying partial differential equations. You're going to be studying the ordinary kind. Just, the ones you'd see just walking around on the street. Nothing special about them. Partial differential equations, they are tough and require a little bit more challenging. Or, as I like to say, they're a little bit more fun. Now, I have some examples listed here. There's something called the Laplace equation and the heat equation. There's many others. But again, you can see that I have partial derivatives relating time and location. Now, I think it's a beautiful subject, very computational, and there's a lot to be said. You will not be asked to find solutions to these, because finding solutions is a very hard thing to solve a differential equation, or a partial differential equation. To verify a solution is very straightforward. So how do you verify? Well, suppose I just say, here is a differential equation. U sub t, u sub xx, and u sub x, u sub tx, and I want them to be equal. To verify says, I'm going to give you a function. Here's the function. U of xt is sine of x plus sine of t. So to verify it, what do? You find these terms. You find the derivative with respect to t. Find the second derivative with respect to x. Again, find the derivative with respect to x. Find the second order, first with respect to t, then with respect to x. Multiply everything together, and you ask yourself, are they the same? And if the answer is yes, it's verified. Well, we're short on time, so we're not going to verify. I'll just write up the solution. And next time, good stuff. So make sure you come.